Well, carbon-13 NMR is based on the same principles that we talked about for proton NMR. There's a couple differences though. So the resonance frequency is about 1/4 of the resonance frequency of a proton, which is 60 megahertz. So it's about 15 megahertz. The other thing is carbon atoms with more hydrogens will absorb more strongly. We'll see that a little bit down below. Now, as far as spin-spin splitting, it's unlikely that we're going to have carbon-13 atoms because they're more rare, but it's unlikely that we'll have them neighboring to another carbon-13 atom. So splitting by carbon is negligible. However, carbon-13 will magnetically couple with attached protons and adjacent protons. So we'll talk about that a little bit more on the next page. Now there's two types of carbon-13 NMR that we're going to be looking at here. So let's just make a note here, and this is our first type. So it is known as proton spin decoupling, or also sometimes called broadband decoupled. So to simplify the spectrum from having lots of spin-spin interactions, protons are continuously irradiated with kind of this noise so that they're rapidly flipping. What happens is the carbon nuclei see an average of all these possible proton spin states. So what this results in is in each different kind of carbon that we have in the molecule, each one will give a single unsplit peak. Right? So we're decoupling. Right? We're not coupled. So there's no spin-spin splitting there. So we see unsplit peaks. Now the position of those signals, it's dependent on the surrounding chemical environment, just like proton NMR. If you recall, having hydrogens attached to atoms that are more electronegative would lead to more of a downfield shift, right? Well, this is true also when we talk about carbon-13 NMR. So if we look down here below, I think you'll see also one difference is the chemical shifts are not so small in their range. For proton NMR, if you remember, the ranges are from about 0 up to 10 to 12-ish or so, right? Most of the shifts are occurring below about 7. Where here we have 0 ppms all the way up to carbonyls, which are at 220, right, ppms. Now, remember, just like proton NMR, only non-equivalent protons give rise to a signal. So this is true also for carbon-13. So let's take a look here at some examples. Now remember, we're looking at carbon-13 NMR, so we're not looking at protons anymore. So it's a little shift in how we're going to be analyzing these problems. So let's start off here with this. How about CH3 carbonyl H? So with this compound here, we have 1, 2 carbon atoms, so this is going to give us 2 peaks. And for that proton decoupled, we'll just see 2 singlets there. That carbonyl being farther downfield than the CH3 of the methyl. Alright, so what about this? Let's look at CH3 carbonyl CH3. So here we have acetone. So how many peaks would you see here? Well, that CH3 here, right, is the same as this as far as the chemical environment. So that's going to be 1, and then that carbon there in the middle is the second peak. So we'd expect to see 2 here also. All right, let's do another one. How about this? Let's go to some line structures now. So what about this guy here? Remember, you can pause this as you're watching it, but let's count this up. So these 2 methyls are 1 peak. So there's 1 there. This is a second peak. That's 2. This is a third peak, right? And then lastly down here at the end, a fourth peak. So this would give us a total of 4 single peaks on that proton decoupled NMR. All right, what about this? So let's put a benzene in here. And then on that, let's put, how about just one bond right there. Right, so counting this up, well, this is a peak. That's 1. Over here, here's 2. Now this carbon here, and then this carbon here, and this carbon right here are equivalent. Right, this carbon here and this one are equivalent, and then lastly we have this one. So counting this up, we have 1, 2, 3, 4, 5 peaks for that guy. So let's do a couple more here. Well, what about this? So here's your ring. What about that? Well, this is going to be like that last one, with the exception that we have an additional CH3 here. All right, so there's 1, 2, 3, right, 4, 5, 6. So 6 peaks on that guy. All right, well, let's take that last structure and add to it. So what if we put an oxygen down here? So now what happens? Well, that's 1 peak. That's 2, 3, 4, 5, 6. And now we don't have this like equivalent thing happening anymore, right? Because we're in different environments. So this is going to be different than that, and that, and that. In fact, they're all just different. When we count those up, should get 10 there, I believe. All right, let's look at another one. So what about this? What if we take a double bond and throw it in there? So what about something like this? This is another problem where we have some symmetry. So those are the same. 1, that's 2, 3, right, 4, and 5. Right, so that would give you 5. Okay, so let's look at another one here. This will be our last one. So why don't we take that last molecule and do this? So now how many do we get here? Well, that last molecule had this symmetry down the middle of the molecule. This doesn't have that anymore. So this CH3 in this case is next to a CH3 here, but down here it's next to a CH3 CH2. So they're different now. So those are different. 2, 3, 4, 5, 6, 7. 7 peaks for that. Again, all singlets for that proton decoupled. Now the other type of carbon-13 that I want to look at with you, so this is our second type, is called off-resonance decoupling. So here the carbon-13 nuclei are split, and they're split by the protons. This is important. Protons attached directly to them. Right, so here that would be split. That H would cause us a splitting on that carbon signal. And because of that, this N+1 rule applies. So a carbon with N number of protons gives a signal with N+1 peaks. So if we look down below at this structure, and often they're given to you this way, there's 2 NMRs here. Right, so this top one that we have here is your off resonance decoupled, spectrum. And the one below down here is your proton spin decoupled. So proton spin decoupled. That's the one where you see singlets everywhere, right? So if we look at the structure, here's 2-butanone here. So let's just label this A, right? Because that's going to be a peak right here. B, C, and D, right? So each of these little blocked carbons would give rise to a signal, right, on our NMR. So when we look at this down below, our proton spin, we expect to see 4 peaks for that, right? And we do. And remember, TMS there is just your solvent, right? So it's a control that you're using as your internal standard, right? Now, when we look up above at the splitting pattern here, let's take a look. So here, right, we ignore that. Now, when we look at this, this is a quartet. So a quartet means that we must be a CH3. So that's what we are. We're CH3. Over here, here's another quartet. So we're a CH3 there, because remember N plus 1. So if that's our structure, CH3, 3 plus 1 gives us 4. 4 is a quartet here. And then lastly over here, we have a CH2. And then way down here at the end, that's your carbonyl. That's your carbonyl. Okay, so as far as the chemical shift on these things, let's take a look at that. So with our chemical shift, let's label something. So this, of course, is B, right? So that's your carbonyl. Now down here at the other end, we have our CH2. So that's obviously our C, because there's only one C there. And then the next are your CH3s. So which one's going to be farther downfield? Well, probably the CH3 that's right here. Since it's more downfield, it's probably closer to the carbonyl. So that's going to be your A, and that leaves you here with your D. All right, so in a lot of ways, carbon-13 really tells you a lot of information. It tells you how many types of carbons you have in a molecule, and it also, if you do this off resonance decoupled, it tells you exactly what you have in your house, right? How many H's are attached to that particular carbon, right? That coupled along with proton NMR, and as we'll see in our future lecture here, mass spec, you can really gather a real good solid picture of what the structure of the molecule is.